Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called boundary of binary tree. So in this problem we have been given one binary tree and we need to return the value of its boundary in anti-clockwise direction. So I would rather explain it by drawing the sketch on whiteboard. I'm not going to read this whole story. So by diagram it will be little bit more clear here. So let's directly jump to this example. So this is 1, 2, 3, and then 4. So if we see here, so this is the clockwise direction, right? And now we need to go anti-clockwise, so we need to go like this way. So this is the boundary, right? So my output should be 1 3 4 2, right? So this would be my output because it went to like this 1 3 and then 4 and 2, because all these are the boundary. Now let's see another example that have been given in the problem itself, and that's 1 2 3 4 5 6 7 8 9 10, right? So 7 8 9 10. Let's go ahead and connect these nodes. All right, so now let's see what's going on here. So anti-clockwise will be here, like this is the anti-clockwise. So now let's go ahead and see. So 1 2, I'm just crossing the nodes that will be the boundary, right? So this is the boundary, right? And like this, right? So observe here we did not cover 5 because 5 is not boundary, it's in the middle. So boundaries means like the border of the binary tree. So let's go ahead and collect our list. So list would be 1 2 4 7 8 9 10 6 and 3. So this should be our output. Let's verify. 1 2 4 7 8 9 10 6 3. All right, so we need to return all these nodes that's going to the boundary from root to left to the leaves and again right. So this is the problem statement, right? And there is no other nodes and there is no other consideration. They have explained the same thing here, that what left boundary means, what right boundary means, and what's leftmost and rightmost. So you can go through this all this detail. So the intention is basically this is the binary tree and this is how we need to traverse, basically from starting from root, go left, go leaves, go right, and then that's it. And that's how we need to collect all these things. So what we are going to do, uh, let's create couple of methods and placeholders and let's do whatever problem is asking us to do. So what we are going to do here, we would be taking first of all our list, and that will be the result. So let's say this is the result, and new, let's say this is array list, right? Now first of all, result dot add, we will be adding the root itself. Why? Because if we go to whiteboard we are just starting from the root, right? And in fact if root is null, that is the base case, right? If root is null, then we just need to go ahead and return result itself, right? Now uh, let's create, let's see I'm having this left method hypothetically, because I'm anyways creating the placeholder here, right? I'm going to explain what it's going to do. So left, let's see I'm having one method. Let's assume that I am having the one method that's called left and that will take care of my left children. So I will do that, and let's say I am having another method that's called leave or leaves, that will cover my leaves, right? All the leaves, right? And let's say I'm having another method that's called right, and that will take care all the right children. So let's create those placeholders first of all. So leaves, and what kind of the leaves I need to take care? So I need to take care of the leaves basically for the left subtree, and I need to take care of the leaves of the right subtree, right? Because I'm having this root. So from the root I would be passing left root dot left. So I would be creating the common method that would be returning the leaves, right? But that common method should take care of the leaves for the left basically and leaves for the right. I need both the leaves, right? So I need this bottom line so that I can add in my result. So this leaves method I need to call 2 times. Hope this is clear why I need to call 2 times. One for the left subtree and another is the for the, so here one is for the left child and another is for the right child of the root. So let's go ahead and do this. Root dot left and leaves root dot right, and let's say I'm having another hypothetical method that's root dot right that will do for the right thing, right boundary. Let's pass this result as well. Result, right? And once I'm done with that, go ahead and return result. That's it. So now this is like skeleton code, like this is how we are planning to do. We are adding root, and after adding root we are just creating one method that will take care of the left boundary children. There is another method called right that's take care of the right boundary children. That's another method that's called leaves that's taking care of the leaves, right? So that's the common method, but we need to take care of the left leaves and right leaves, right? Because we are having the root, right? So it's easier or it's convenient to pass just the left child and just take care of the left side of the leaves and the right side of the leaves, and then again just go to the right children. So this is the skeleton. Now let's see that how we are going to approach this thing, right? So let's create this binary tree again. 4 5. So this time I'm just creating another hypothetical binary tree, right? This is not exact same as earlier. So now let's see. And so this is like very basic case, right? So in the earlier example, if we see, we were having the 5 here, and if we can make the similar thing here as well, let's see. So if we are having 7 and then 8. All right, so I want to make sure that just consider this test case, so that in this test case the reason is basically in this case it will go like this, leaves, and then like this, all the boundaries. So 5 it will not consider, right? So this is one test case. Another test case may be like simple, just go ahead and consider all. So for example, if we don't have 7 8, we need to cover 5 as well. But if we are having children of 5, then 5 is in the middle, it's not boundary, so we are not going to consider 5 in this particular case, in this particular test case. All right, so root is straightforward, we already added root. Now the left method, what it should do, it should consider all the left children, right? So what we will do, we will just traverse root dot left, right? We will just traverse root dot left. If root dot left is there, then go ahead and add, right? So root dot left is 2, we will add 2. Now root dot left is 4, but we can, if we add 4, will it be right or wrong? So here 4 is leaf as well, right? And our left method is dedicated to add the left boundary children, right? But it does not care about the leaves, right? Because for the leaves we are having the separate method. So we need to consider, we need to add another base case. If this is the leaf node, then don't add. If it is not leaf node, then just go ahead and add, right? So this is one case that we have to consider. So 4 we will not add, right? So we will just add 2. Now let's go ahead and consider this case. So let's say 1 and then 2. Let's say I'm having only this binary tree. So what my left method will do in this case, my outputs would be 1 and 2, right? But what my left method should do, so it will go left, and that is null, right? And if it is null, then it should consider the right child. So it should consider 2 itself, right? So what ideally it should do, or in fact what this is like, I mean in this particular case, in fact right method will also consider this, but let's make another example. Here is 1 2 and then this 3 and then something like 5, or I can create more. So what it will do, it will just go left 2 and left side it's traversing again, then left is null, then ideally it should go to right? And let's say this is not leaf node, this is having 7 or something else. So ideally it's not, if it is not leaf node, and then basically it should go to right. So this condition also I should take care. If left is null, go to right, and if left is not equals to null, then go to left itself, because it's a boundary, right? So if left is null, then boundary will be the right child, so it should go to the right. So these are the couple of observation. One consideration, it should not be the leaf when we are writing the implementation of left child and right boundary children. And another consideration is like, if left itself is null, then basically go to right itself, because we want to consider the boundary. So let's go ahead and do that. I think once we convert the same idea into the code, then might be it will be little more clear. So tree node, or in fact this is void, so we are just filling it here, right? So let's go left tree node root and result. So list of integer result. So the base condition, I mean general base condition, if root is null, then go ahead and return, right? So here I am also starting with a skeleton, and res.add, go ahead root.val, right? Why? Because we want to collect all the left children, that they are boundary, they are on the boundary. Those children we want to consider, they are on the boundary. So let's go ahead and recursively call this, and in fact we need to pass if root.left equals null, right? So we have seen this case, right? So this is null, so this guy is null. If this guy is null, means the boundary is 3. So let's check. If left is null, then go to right. So if left is null, then go ahead and root dot right and then result. Else means left is not null. So let's go to left. So root dot left and then result. So we consider this case. Now let's consider this case as well. Let's say if it is right, it went to right, but this guy is leaf, right? We don't want to consider leaf, right? So let's avoid 7, because we are having the dedicated method that's called leaves, and that's responsible to collect all the leaves, right? So let's avoid the leaves as well. And how we can avoid? We can just check if it is leaf, right? And how we check leaf is if it is leaf or not. If both left and right children are null, then they are leaf, right? Such nodes are leaves. So if left is null and right is null, then go ahead and return. And in fact root is null, then it does not make any sense. This is just the base condition, I mean main base condition, original base condition, and we are just avoiding the leaves as well. So I'm just copying pasting the same method, similar method, not exact same, for the right. So because we will be doing the same thing for right as well, concept would be same. Like for example, if right is null, right? So If right is null, then we would go to left, right, the similar way. And if right is not null, then basically we are going to have we are going to go to the right itself, right? So in the similar way, if left is null, we are going to the right because that's boundary. And let's similar case, like if this guy is having some number 9 and then 11, so this guy right is null, right? This is null. So if this is null, it will go left because we need to consider, because this is the boundary, right? Because this does not have, this is null. So that's why we will go, if right is null, go left. Otherwise right is not null, then consider right itself. This is one thing. Leaves also we already added into the base condition, so we should be good with that. Another thing to consider here is, because right, if you observe the pattern, if I go to another slide here, this one, so for the right we are going bottom to top, right? For the left we are going to the top to the bottom, and that's the reason we are just adding before going to the recursion, right? So top to bottom. But for the right we are going bottom to top. So if we are going to bottom to top, we need to add our these nodes after going to the recursion. After going to the recursion means after recursion is done, right? Then only we need to add. So basically we don't need to add 3 and 6, but we need to add 6 and 3. So ideally what it will do, it will just go in the recursion of 3 and then 6. So recursion stack will be like this: 3 and then 6. Once recursion is done, we will be adding 6 and then 3, right? So it will be added like this in the recursion, and that's what we want to do. So let's go ahead and add it here. So we are done with the left and right. Let's implement leaves. So in the leaves, let's node, let's say this is root, or in fact let's say it's node, it's not root, because either it will be root dot left or it will be root dot right, right? So the similar thing is, if node is null, then go ahead and return, right? Return nothing because it's void. And res dot add node dot well. So when we want to add this, we want to add this if node dot left is null and node dot right is null, right? If both the children is null, both the children are null, then they are eligible for the leaves. So let's go ahead and do this. Node dot left leaves, call for left and right, and once we found, once we reach to the bottom, then just go ahead and add, collect those children, right? That's the idea. And we also have the list here. So list of integer result, and this is result. So this is how we are planning to solve this problem, right? So we are starting from root, we are going left, we are going bottom, that's leaves, and we are again going back to the right. So left and right implementation is pretty much similar. The only difference is right we are going bottom to up. So bottom is like just add after recursion, right? And in the left, add in the list before going to the recursion. That's the only difference. Otherwise they both are conceptually they are same. Leaves are super simple because we are just collecting the bottom. So if the children are null means root dot left and root dot right, they both are null, then only add, otherwise don't add, right? So let's go ahead and quickly check for the compilation error if there is any. And that should be so bad operand. Let's see. Okay, that makes sense. So generally I focus to explain the approach, and that's why I get syntax, lot of syntax errors as well. So let's see. Cannot find a symbol. That's result. Let's go ahead and see the other errors. Alright, so this is copy paste, so that's obvious, and that's the drawback of copy paste. So res, let's go ahead and change this guy. A lot of typos, leaves. Alright, so we need to pass here the result is as well. So trying to correct couple of syntax errors. I think it should be fine. I can check other test cases as well, but before that, let's go ahead and see what is going to the time and space complexity. So time complexity is because we are going, basically we are checking each and every node, right? So I would say it would be roughly linear time. We can argue like if it is a pretty huge binary tree and there is a lot of these middle nodes, then there will not be like there will be lesser than the linear time, but as we calculate the approximate time complexity, then it would be linear, because anyways we are just traversing through approximate each and every node, right? So I would say it's order of n. Space complexity, let's assume it's flat tree, like if it is like it's having pretty flat, then we are going to traverse each and every node, right? And implicit stack, we are just in the recursion itself, we are just maintaining, storing all these nodes itself, so it will be linear as well. So let's go ahead and see. uh, so let's see this 15324, so it failed for one test case, but no worries. Let's see what's going on here, right? So res, we already added the root, and then root dot left, and oh, so root dot right, that's looks like true, and then result. And let's quickly verify whatever we have discussed, that we are taking care of that. So root dot left is null, then go to the right, and that's true. And that's the problem. I mean, that's obvious with the copy paste, and that's the, I mean, I highly recommend that don't do copy paste until unless it's really needed, because a lot of time it happens like copy paste, we forget to correct the things, but here the, to save the time, I just did the copy paste. But anyways, it's working fine now, and hopefully this concept is clear, that how we can divide one problem into the chunk of basically in the chunk of methods and models itself. What happened, let's see. I'm just reloading my plane. So before ending this video, just quick summary is basically just because this is a boundary, so we can divide this problem into the subcategories. Just first of all, add the root, just go to the left, go to the bottom, right, and then just go to the right. So these are the three major component. For the implementation perspective, for the left and right, just consider two cases. Once going to the left, just consider like if left is null, then we have to go to right. So this is one case. Another case is just avoid leaves means avoid all the children, I mean all the bottom children, that they don't have further children, right? So avoid all the leaves. So though they will be the part of base condition. The difference between the right and left is, right, we are going from bottom, so we are adding like from bottom to top, and from left we are adding from top to bottom, and that's why we are adding in the list basically after going into the recursion, right? In the leaves, basically simply it's super simple. If it is leaves in the bottom, like if left and right both are null, then only add, otherwise don't add. So this is just a quick summary, and this is just a breakdown, that this is how we can break down and we can just solve this problem. Hopefully this was useful. Thanks a lot. Have a good one. Bye.